All right, now we're going to turn to DNA sequencing. So DNA sequencing is a modified form of PCR, at least how it was originally conceived of, that allows you to actually determine the order of the nucleotides on a DNA strand. So before we talked about looking at the size of a PCR product, but with a slight modification, you can now actually determine the nucleotide sequences. So there's many different technologies. So there's dideoxynucleotide sequencing, there's Sanger sequencing, and then there's new next generation sequencing technologies. So the next generation sequencing technologies is what makes current sequencing so cheap, and there's new approaches that continue to be developed. So we are not going to cover any sort of next generation sequencing technologies today, and we're mainly going to focus on dideoxynucleotide sequencing and then a little bit on Sanger sequencing. And so the secret of this, the way that Fred Sanger originally conceived of as a way to determine the order, is by using a chemical trick, using a modified nucleotide called dideoxynucleotide. And so this is very similar to your normal deoxynucleotide, but instead of having an OH at the 3' end, you replace it with a hydrogen. And so what happens is this causes the DNA synthase to terminate. So normally you have a nucleotide. This is obviously for DNA. So if it was an RNA, there would be an O there. So this is a DNA, a deoxynucleotide. You have the 3 phosphate groups attached to the 5' carbon, and then attached to the 3' carbon is an OH. And so if you want to connect two nucleotides together, you need to use the oxygen and the hydrogen on this, and these make a chemical reaction with a group right here. This O is necessary because a byproduct of nucleotide formation is H2O. And so you need that oxygen molecule to produce H2O from this reaction. So if you have a dideoxynucleotide, it does not have this OH. So it is able to link up to this nucleotide right here because the 5' end is not modified, but it is unable to allow another nucleotide to come into play. So this is what we mean when we say that it is a chain termination. So if you have this incorporated into a PCR reaction, if this gets incorporated, then it's going to stop that particular chain. And so we go over this in more detail in the activity, but the idea is that you can have specific nucleotides. So one of the things you can do is make specific nucleotides, and this I'm referring to the N here, that are dideoxy in nature. So normally we have a mixture of DNTP that we used for PCR, and now instead of using DNTP, and just to make this explicit what DNTP is, it's a mixture of 4 nucleotides. So there's the DATP, there is the DCTP, there is the GTP, I'll just shorthand this, and then there is the TTP. So what happens if you replace this ATP, this DATP, with DDATP? And so let's say we have a sequence So if we use our normal DNTP mixture, we can do G, G, C, G, T, A, and then continuing on through. But now, if instead we use the DD ATP mixture, basically this goes on until we reach the first A. And so these 3 nucleotides cannot be incorporated. And so this creates a set size. So we know, starting from, if we have a primer over here that we started it from, if we know that it extends 6 bases onto this primer, we know where the first T is of the sequence, because that is where an A gets incorporated. And then all of a sudden the termination occurs. And so if you ran this out on a gel, what you would have is, a specific size band. And you can do this with all possible nucleotides. So in this case, we use DDATP. But you could also do a reaction with DDCTP, where DCTP is replaced. And so in that case, you would have a completely different band. You'd have a smaller band where this would happen. And so this forms the basis of the idea behind DNA sequencing, is that you have this dideoxynucleotide that terminates a reaction, and typically you have maybe 4 mixes. So in the first generation of this technology, you had 4 different reactions, each one with a different one in there. And then if you spike in a small amount of this instead of making all of it, so if you have a mixture that has DATP and DDATP, what happens is that you can, some of the sequences read through because they incorporate the DATP, and some terminate. And so some of them would go on to the next one. So I think this activity will hopefully make this all clear. But if you have a mixture, then you can start to see kind of multiple bands for each thing. And so in combination, you can then actually figure out the sequence that way. So this technique was then modified, and the modification that was very important was to go from just using DDNTPs, but to now incorporate fluorescent dyes that are also labeled onto these DDNTPs. And so this allowed the large-scale genome sequencing that made it possible to sequence the human genome. And so the idea behind this is now we not only have DDATP, DDCTP, DDGTP, and DDTTP, but we've also incorporated a unique dye into each of them. And so this one is labeled red, this one is labeled blue, this one is labeled green, and this one is labeled yellow. And so again, we spike in a small amount of that. And so what you end up having is you have extensions that terminate at different points. And depending on which nucleotide it terminates on, determines the color of the dye that is incorporated into it. And so you do this reaction, and so you continue to have products that stop right away. You have products that make it through 1, you have products that make it through 2, and so on, until you're left with a mixture of about 500 different sizes. So after you do the sequencing reaction, you're left with 500 different size products, and each one has a different color dye incorporated into it depending on the nucleotide that terminated it. And so if you run these through a capillary gel, this is going to run the fastest and the largest is going to run the slowest. And then simultaneously you have a laser and a detector that allows you to determine the color. So as this set of products runs through a gel, so this is just it's a gel that's in like a capillary tube is why it looks like this. The different bands will run past the detector at different times, and so you're left with what's called a chromatograph. And so this is the color of the product, the color at a given time. So this is the first one that goes through, and then this is the last one that goes through. So this technique has allowed us to actually do DNA sequencing largely automatically. So a large majority of the DNA sequencing approach is now all done automatically, where the capillary gels are preformed and you load them in there, and then you have a chromatograph, and this can be read automatically to predict the DNA sequence.